So let's start our derivation of the Fourier series. Now this is quite mathematical, but it's well worthwhile thinking about the Fourier series in this manner. It answers an awful lot of questions that you may have in the future about the Fourier series, even questions you haven't thought of at the moment. So we've seen previously that we can write the Fourier series out in this form here, and we know that these values of cos nx and sin nx, these are known quantities. But the a0 and the ans and the bns are unknown, and we want to find a method of working out what those ans and bns have to be in order to approximate a function. In this case here we're going to use the square wave as the example. Now what we're going to do through the rest of this video is we're going to look at the idea of a function, but a function as a vector. Now if you haven't seen that before, it might sound strange to you. You might think of a function and a vector as being two different mathematical things. But a vector is a very general mathematical thing, and we're going to look at it and we're going to see how we can represent a function as a simple point in an n-dimensional vector space. So how can we think of a function as a vector? So first of all, we think what a vector is. So a vector is defined as a directed line segment. So we've seen a vector here in blue, and we're used to seeing it in, say, 3 dimensions. So it might have an x, a y and a z axis. And you would say here, in this example here, we've got a vector 3e1, 4e2 plus 2e3. So what we're really saying is we would come along 3 in the x-axis, along 4 in the y-axis, and then we would go up 2 in the z-axis. But we don't use the x, y and z. We work out, or we determine the directions via multiples of a basis vector. So these vectors here, e1, e2 and e3, so these point along the x, y and the z axes. So these are vectors of unit length, so length 1. So the vectors here are normal to one another. So normal, loosely we could say, means at right angles. And they're length 1, so they're normalized to 1. So we then say that these are orthonormal vectors. And we actually say that e1 hat, e2 hat and e3 hat form an orthonormal basis. And in order to work out each vector, we just multiply this orthonormal basis by a scalar coefficient. So the scalar coefficient here is simply the 3, the 4 and the 2. So that's our vector. So how can our function then become a vector? Well, let's look at this quite loosely, but it gives you a good indication. Let's imagine we had this function drawn out in blue. Well, let's say the function wasn't actually a continuous function, and it was only a discrete function with only 3 points. So the 3 points are x1, x2 and x3. So let's say the height at x1 was 3, the height at x2 was 4, and the height at x3 was 2. Then this little digital function would look like the same as this vector here. It would have height 3 at x1, it would have the height 4 at x2 and height 2 at x3. So potentially we could say that this directed line segment, or this vector, or a single point in this 3-dimensional vector space would represent this simple digital function which is only 3 points. But it means that in this 3-dimensional space, all the points in the 3-dimensional space can only ever represent a function here which has got 3 points. The functions that we want to represent aren't discrete functions. The functions we want to represent are continuous. So you could imagine extending this up to higher dimensions. So if you wanted to represent 4 points, you would need another basis vector. Of course, we can't draw that out physically because we've only got 3 dimensions in order to draw it out. So you may be then for asking yourself, well, how do we define the idea of a right angle if we've got a 4th vector there and we've nowhere to draw it? Well, these are something we're going to come to whenever we work through the rest of this video and the next video. So if we were wanting to represent a continuous function, then we could imagine having a vector space that has got infinite dimensions. And we could imagine a function then being represented by a single point in that infinite dimensional vector space. Now that might be quite hard to get your head round it if you haven't thought about it before. It's one of these things that's worthwhile taking your time and just mulling it over. And it takes just a little bit of mathematical maturity to get away from the idea that mathematics can only describe things in the 3 dimensions in which we live. It doesn't. Most of the most interesting mathematics involves much higher dimensions. So this is a neat little way of thinking about a function as a vector. Let's continue and we'll see how to work out the constant terms for our Fourier series. So if we were to take a function f of x, and if we were to sample it from 0 to n, and if we let the number of samples tend off to infinity, then we would have in effect the function f of x. So we could say then that the f of x could be described as the scalar coefficients an, so that's the heights of each of the elements, and the value xn, well, xn is the nth element. Now if we think about the nth element is equivalent to the orthonormal basis vectors, then we could say that when we add up all of these an xn's, they're equivalent to that function f of x. But equivalently, we could say that is the same thing as the vector a. So we're really saying the vector a is just like a1 e1, a2 e2, a3 e3, so on and so forth off to infinity, and we're saying that the function then is equal to an xn, which is a0 x0, a1 x1 off to infinity. And if we think about this, xn is the same as the e1, e2, e3, then we can equate a function as a vector. So you're probably sitting there scratching your head and thinking, oh my, what's going on here? Why is he telling us all this stuff anyway? Well, there is a reason for doing it, and the reason for doing it is that we can find the scalar coefficient of a vector by using the dot product. Now if we can think of a function as a vector, then we can equally find the scalar coefficients here, the an's, by using a dot product. So in fact we can find the scalar coefficients of the Fourier series if we think about the function as a vector. Now that's a lot of words, and I think it's best seen by an example, and you see us working through it, so we'll go through that over the rest of the video. So let's imagine we have this problem here. Given a vector a equals a1 e1 hat plus a2 e2 hat plus a3 e3 hat, we want to find this scalar coefficient a1. So I've got this drawn out, and we'll see that if we come along a1 e1, and we come in a2 e2 and got a3 e3, we've got this vector here in blue. Now in order to find the scalar coefficients, what we do is we take the dot product. Now if you're unsure of the dot product, we're going to go over it just in a second, okay, and it will all become quite clear. So if we want to find the scalar coefficient a1, then what we do is we take the dot product of the vector with the e1 hat. If we wanted to find a2, we would take the dot product with e2 hat, and if we wanted to find a3, we would take the dot product with e3 hat. So let's look at finding a1 first of all. So a1 dot e1 hat will be a1 e1 hat dotted with our e1 hat, and it would be a2 e2 hat dotted with our e1 hat, and our a3 e3 hat dotted with our e1 hat. The e1 hat dot e1 hat will give us a value of 1, so that'll be left with a1, and the e2 hat dot e1 hat will give us 0, e3 hat dot e3 e1 hat will give us a 0 as well, so we'll just be left with our value of a1, which is this length here, which is what we've been looking for. Now, when we were looking at the multiplying two vectors together, so we'll just go with this dot product here now. When we're going to multiply two vectors together, a vector's got a direction and also a magnitude. So how are we going to multiply them together? Well, there's several different ways of doing this, and one of the ways that is of use to us is called the dot product. So let's say we've got this vector A here in this direction, and there's a vector B here, and we want to multiply vector A by vector B, or equivalently vector B by vector A. So what we can do is we can take the magnitude of B, which is actually in the direction of A. So there's a vector there, that's a vector B, and we're saying what part of that vector B is actually in the direction of A? Well, the part that's in the direction of A, if we drop the perpendicular down, would be this little blue line here. And then we multiply the length of this line here with the length of vector A, and that gives us the dot product, which is just a scalar, it's just a number. So let's look at this example here. Let's say both these vectors are sitting and they're perpendicular. Then we ask the same question. What component of B is in the direction of A? Well, in this case, the component of B in the direction of A is 0. There's no component of B in that direction. Now, if this was a line that was slightly off here, then there would be a small component in that direction, or even if the line was in this direction, then again there would still be a small component. But if the two vectors are sitting orthogonal, which means sitting in this case at 90 degrees, then there is no component of this vector in that direction, so it means that the dot product would be equal to 0. But if both of these vectors were lying one on top of the other, and let's say each vector had length 1, then when we took the dot product, the component of one vector in the direction of the other would be just that vector, so it would be 1 times 1, which would give us a value of 1. So it means that if we were to come up here and look at our orthogonal basis, then if we looked at E1 dot E2, well, that's going to give us a value of 0 because they're orthogonal, and E1 dot E3, again they're orthogonal, will give us a value of 0, and E3, E2, they're orthogonal, will give us a value of 0. But if we looked at E1 dot E1, that would give us a value of 1, E2 dot E2 would give us a value of 1, and E3 dot E3 give us a value of 1. And we can use that to solve this example. So we've taken the E1 dot E1 and it's given us 1, the E2 dot E1 is given us 0, and the E3 dot E1 is given us 0 as well. So that's how we solve this little problem. Now, we're still sitting here maybe scratching your head and thinking, so how does that help us? Well, we'll see that on the next slide, and on the next slide here it'll all really become apparent as to why we've gone through this whole process. So everything so far has been leading up to this point here. If we can take our Fourier series, and we know we're looking to find the values a0, an and bn, so we can think of these as scalar coefficients, And then if we can think about the cos nx and the sin nx as forming an orthonormal basis, then we can use the process that we've seen previously of taking the dot product in order to find these scalar coefficients. So really we're looking at a0, an and bn as being the scalar coefficients, and the cos nx and the sin nx as forming an orthonormal basis. But the question that we have now is, how do we define this dot product? It was simple enough before to find the dot product on a simple real number line, but now we don't have a real number line. Instead of replacing the real number line, we have sets of functions, cos nx and sin nx. So the next video we'll go ahead and we'll define this dot product on this new vector space of functions which we have just created, and from that we'll be able to work out the values of a0, an and bn. Thank you for listening, and goodbye.